All right, welcome back. Where we left off in the last module was looking at the individual local optimizations that compilers are capable of doing. And there we were able to sort of trace through in the pseudocode format the type of optimizations that are possible by looking at constants and how they propagate, by looking at operators and how they could be reduced to simpler operators. Next, we're transitioning to looking at loop optimizations. And I start the slide off here by saying loop optimizations are arguably the most important set of optimizations. And it's a bit of a rhetorical question. Why is that the case? Well, think of the code that you write, and it's always going to be containing loops, right? Certainly, if you look at engineering and scientific code bases, you see these blocks of multiple nestings of for loops within loops within loops, and that is extremely common as we iterate over multi-dimensional arrays in our code for some simulation or other CAD or other tasks that we have here. But all of our code, if we look at it, is fundamentally running in loops, right? We're always either having a straight line, single one-shot code that just starts and ends and doesn't do anything terribly interesting, or we're iterating on something, right? We're waiting for an event, and then we're processing that event, and then we're doing something with that event that happens. So one way to answer that question is why loop optimizations are more important than those local optimizations is because our code is running in loops. And the general rule of thumb that people follow is the 90-10 rule, which is 90% of our runtime of an application is spent in 10% of the code, and loops are the reason for that. Same reason back why in 381 we would care quite a bit about control logic, because we're constantly running branch instructions, and so having those be relatively efficient and fast is important. For the same reason, the compiler and the research in compiler and the optimizations that are designed for compilers has really focused on those loop optimizations, because 90% of our time is spent inside those loops. Any improvements we can make there can have a bigger impact on our overall performance. There are a number of different loop optimizations, and if you look at a compiler textbook, you'll find 40 or 50 variants of the same kind of theme. We will look at a few today. I don't think our goal is to become an expert on how to apply these optimizations. Raising our awareness of what is possible in the set of optimizations is a good outcome for us, I think. A basic understanding of the trade-offs involved in loop optimizations. One thing you'll see repeated here today is when I ask, will this optimization improve performance or not? The answer is very often, well, it depends. It's not as clear-cut as some of those previous local optimizations. We had an instruction, we were able to get rid of the instruction, that's our dead code elimination. Yes, of course, that's going to make our performance better. For loop optimizations, it's more of a curve, and it's more of a middle ground that we can find between how aggressively we want to apply the optimization and whether there's ultimately a performance benefit of applying that optimization. Let's go through a few of those examples. The first example I have here is referred to as loop unswitching. It's a bit of a funny term, but the idea there is that you have a switch in your code. You have a condition inside your loop itself, and we can take that conditional inside the loop and remove it and put it outside of the loop instead. So in the example we have here, we have, there's a little bit of a Fortran-like pseudocode here. We have a doubly nested for loop here, and inside that innermost loop, and again, if we think about our complexity of the code, it's that innermost loop that's going to be running a lot. That's part of our 90-10 rule here for this code here. Inside that innermost J loop here, we have a conditional. If t of I is greater than 0, do something relatively complex. It doesn't necessarily matter. Otherwise, do something else. Even as software developers, I think we can look at that code and realize, well, did that t of I branch need to be inside that inner loop or not? Right? There's no dependencies on J here. We can actually check and see that t of I condition and have it be outside of that outer or that inner loop versus inside that inner loop. As a software developer, you yourself may be finding that optimization opportunity yourself just in analyzing your code. Compilers are capable of doing that analysis as well here. So in this example, because we've been able to move this t of I outside of the loop, we're effectively replacing that inner loop body with two copies of that inner loop body. One for which the case was true, and we took the if side, and the other version of the loop for when the case was the else, when t of I was less than or equal to 0, and we would do just the initialization into 0 here. So think back to CPRE 381. I know that was not pleasant times for everyone, or whatever class that looked at software optimization that you took previous to this. We certainly did cover this in 381. And think about, well, why would this actually make performance any better? Again, as I mentioned, right, the branches are what are critical, can become critical for our performance. Every time we have those if statements in our code, we have a branch, and we have a data dependent branch here. We talked about that as control hazards in our code. And there's all sorts of architectural tricks that people have added to processors over the years to allow those branches to not be as painful as they were if you didn't apply any of those approaches. But still, they incur some pain. We have long and deep pipelines, and when we have that branch inside our pipeline, we have to account for what the next instruction is supposed to be. If we're not careful, we wind up fetching and potentially executing a whole bunch of instructions that we actually weren't supposed to execute because we took the branch or assumed the branch should be taken and it was not actually taken. So looking at this refactored version of the code where loop on switching was applied here, we can see the advantage potentially is that for that actual if statement and the branch instruction that corresponds to in our assembly, we're actually going to be executing it significantly fewer times, right? If this is an n squared execution of the if statement here in the corresponding branch, here it's only order n, right? Because it's outside that innermost loop now. We just don't have nearly as many of those branch conditions as we did in this example here. And reducing the frequency of conditionals in our code will lead to performance. Nothing on the order of magnitude and performance improvements we saw in the motivating example where we were looking at cache effects, but conditional effects in our control hazard logic can definitely make an impact on performance as well. In terms of whether or not our overall performance is better, whether this is something we should always do or not, this is the first example where the answer is really, it depends, right? If you yourself were refactoring the code from the version on the left here to the version on the right, you can make the argument certainly for performance for the reasons we just discussed. Code, arguably, this is more of an opinion than a true fact. Arguably is more complicated on the right now. It depends. It depends on your understanding the underlying logic model of what the code is trying to do. Certainly, it is more lines of code. That is not debatable here. So whether more means more complex or not, the version on the left is a nice, tight, doubly nested for loop. The version on the right now has this conditional for loop. It's more lines of code, more things to debug, more potential places where you possibly inserted a bug. If later you realize, it should actually not be from j equals 2 to n, it should be j equals 3 to n minus 1. That was a code change that you had to make for correctness purposes. In this version on the left, you make it one place, and on this version on the right, you have to make sure you make it two places. Compilers will take care of that correctness update for you as it applies the optimization, but arguably the code on the right that results is more complex than the one on the left. And it's not just complexity that potentially could lead to an impact in performance. Just having more lines of code and correspondingly having a larger executable size in a very small amount here, right? You can't look at lines of code and say exactly just by that how much longer the number of assembly instructions would be, but it's longer in this example here. We're doing more stuff. We have 2 copies of that same for loop here. Larger code size, if we think back again to our CPRE 381 days, larger number of instructions, potentially less spatial and or temporal locality in our instruction memory, potentially more cache misses there. Even if we don't look at that second order effect of performance by having a larger code size, for our embedded systems where every byte may be precious for us, by applying that optimization, we've increased our instruction memory needs here. Potentially, we've not met some other metric that our system requires. So for these type of loop optimizations, and as we go through a number of them here, I'll go through them somewhat quicker than this first example, that's the trade-off. In theory, it makes sense. End result tends to be an uglier looking piece of code or a more complex looking piece of code, and then also a piece of code for which the instruction memory has grown. Whether performance has improved or not, we think it will. We can't say for certain until we actually test it, until we actually measure it here. Another example of a loop optimization that can be applied is referred to as loop peeling here, where we separate either the first or the last iteration of the loop off from the rest of the loop here. In this example, though, just as a motivating example, it doesn't really show why there'd be any benefit of doing so. We'll see some other examples in which by applying loop peeling, we've led to potentially a performance improvement here. This example just shows the functional equivalent of having applied that loop peeling, where we have our I to N loop here, and we've replaced it with a version that takes the first iteration of that loop and then separately does the rest 2 to N iteration of that loop. There's no reason to believe this version on the right would actually be improved from a performance perspective versus this version on the left. This is just the type of analysis that compilers are capable of doing. Take the first few, last few iterations of the loop and peel them off and separate them from the remainder of the loop to potentially enable other optimizations that can be possible. Index set splitting is another common optimization that can be applied here. And again, these are all synthetic examples, but this is the type of thing that our code tends to have inside it, right? Where we have a for loop where there's the steady case, and then there's the exception case, where in certain scenarios, where in this case I equals 1 to 100, we always do the vector addition, but only if I is greater than 10 do we actually do some additional manipulation of our arrays there and store an additional value. The idea being in this optimization as applied, as opposed to trying to complete everything in one single relatively complex loop, we take the index set, the indices for which we iterate over an array, and we split it into its 2 separate portions separately. So from this version on the left, which is a single loop that has a little bit of complexity in there, we've split it into 2 separate loops, each of which are relatively simple. This is certainly going to allow us to potentially apply different optimizations. For the version on the left, the compiler is going to be limited in the type of local optimizations that are possible, like we talked about last time. Things like replacing the operation with a copy of the result, things like dead code elimination, because when analyzing this loop, it can't guarantee that whether it goes into this statement or not. That's a branch inside our control flow graph for that loop. Whereas for this one, although the examples will be fairly limited what we could find inside this illustrative example, we have 2 separate loops, each of which are very straightforward, that allows us to apply other local optimizations that are inside here. Like with these other examples, we did go from a single loop with a little bit of complexity to 2 completely separate loops. As we continue to do things like index set splitting and index peeling, we will potentially increase the size of our code here. Another example is scalar expansion, where we look at the dependencies that are inside a loop, and by promoting that scalar to potentially an array, we transform that dependency into one that's actually not a true dependency here. So this is a little subtle. Let's go through it a bit slowly here. We have a loop, which is creating a temporary variable t here, and then it's using that temporary variable t in the next line, right? And going back to CPRE 381, that's our read after write dependency. Very natural thing. That's data dependency. It can potentially lead to hazards. It's just a natural byproduct of writing code that has dependencies here. We can't avoid it in this example. It's always going to be there. Temporary result, using that temporary result in the next line. But because this is a loop, we also have some really false dependencies that aren't intended by the programmer. Because we've defined this variable, this scalar, this single variable t here, as we go from iteration I equals 1 in the loop to I equals 2 and etc., we wind up having all sorts of other dependencies, right? Not just between writing of t and reading of t right here, but between writing of t in the first iteration and writing of t in the second iteration. And all sorts of other permutations, right? So we have the somewhat natural, unavoidable read after write dependency between these 2 t's here, but we have all sorts of read after read dependencies and write after write dependencies and write after read dependencies because of all the iterations of the loop. You name the dependency, this code example on the left shows it here. The only one that really matters from a functional correctness perspective in terms of the programmer's intent is that initial read after write dependency. We can't necessarily fix that or do anything from the compiler's perspective for that dependency. But for all those other sort of false dependencies here, by promoting that scalar into an array, we remove those additional dependencies, those dependencies that are only happening because as we iterate through the loop, we're repeating the same variables that we're using through that loop. And that's all that's happening here. The code's a bit more verbose than it necessarily needs to be to show the point, but okay. The idea being that instead of being a single scalar for every iteration through the array, we have an array to store those temporaries. So an array of temporaries here, so we have to allocate those arrays, that's fine. And so as we go through the loop, instead of t as the temporary variable, we have effectively a t of I, or in this case, tx of I as our temporary variable here. So now we still are going to have that fundamental read after write dependency. That doesn't go away, right? From tx of I being written to tx of I being read on the next line of code that we have here, but all those other false dependencies are now gone, right? Between tx of 1, there's no dependencies between that and tx of 2. It's a different variable, or it's a different location in memory. Those dependencies are now gone. For correctness purposes, just as we also only allocate the array if we need to here, if this code really did depend on t having the value at the end, we would make sure we actually set t to have the value. But even if we don't do that, I think we can convince ourselves that the value of c at the very end of this code executing is the same as in this example over here. So that removes all those false dependencies there. And by getting rid of those, that opens up all these other sort of optimizations that are possible, right? In terms of what registers we're allocating to things, what type of parallelism we could potentially extract from this, right? In this version, there's that iteration to iteration dependency. We really have to wait for I equals 1 to be complete before we can execute the I equals 2 loop. But in this example, that's no longer the case. We now have n iterations through this loop, and all n are completely independent of each other. However we want to parallelize, whatever architectural features we have to take advantage of instruction level parallelism are now fair game for this example that we have here. The disadvantage, such as it were, for this example is a little bit more clear than even the other ones. Yes, the code is more complicated again, but also we've had to allocate more data memory in this case now, right? It is much less data memory efficient to do this example versus this example. In this one, you can wave your hands and say, well, I already have a few arrays of size n, I'm just adding one more. But as you take this approach and apply it to multiply nested deep loops that we have here, it can potentially become prohibitive, the amount of memory you would need to be able to do that promoting of scalars for temporary variables into arrays of temporary variables. Another example here is referred to as loop fusion. So fusion, we combine things together, and that's exactly what's happening in this example here, where we take two adjacent loops, and instead of having them be separate loops, which we saw was potentially itself a performance optimization, we actually want to combine those loops together. And we do so if we can do so without violating any dependencies between those loops here. Right, so for this example, we have three separate loops that use effectively the same I equals 1 to n bounds. And we can potentially fuse them together, right? Generate a single loop that contains the bodies of the three individual loops that we have here. So instead of three separate, we have just one loop here on the right. And we can proceed based on our knowledge now of loops and control hazards. We can see the potential advantages there, right? We've gotten rid of all those other for loop code, all the branches, all the variable initializations, all the things that are required to maintain three separate loops. We've now combined those all into one loop. So in terms of potential disadvantages, well, we talked about implications on locality are still there. There's issues potentially with data dependencies. It does change the relative access pattern of our memory, right? If we were to look at the access pattern for data memory in this code on the left here, we'd access B of 0, then A of 0, B of whatever, B of 1, then A of 1, B of 2, then A of 2. Whereas this example has a different access pattern, right? B of 1, A of 1, A of 1 again, C of 1. That seems like an advantage, having fused the loop for potential temporal locality in A and potentially in C here. But that may not always be the case as we apply that loop fusion. There's all sorts of techniques that the compiler can provide. Basically a linear algebra formulation of the data access patterns of our loops to be able to determine whether this would be a good idea to do or not. So potential disadvantages is the locality implications not illustrated in this example. But I'd like you to pause for just a minute and think about this example on this slide here where we've applied loop fusion. Are there any other potential disadvantages of having applied this loop fusion to this example? Take a minute, pause if you can. I assume everyone paused and didn't just, speed through this and actually thought about it. Can we see it? Right. In this example here, the fusion is actually, illegal. It leads to the one thing that compilers are sworn to protect, right, which is the functional correctness of our code here. We have to be very careful of our data dependencies between the loops. This from A of I to A of I is a read after write dependency. By fusing these two loops, we still have the same order of our read after write dependency. They're just closer together. That's potentially a good thing. It leads to data hazards, maybe better for cache. We would have to run the code to know for certain. Between C of I and C of I plus 1, we also have a read after write dependency. Now, by fusing that second and that third loop together, we've actually broken the order of that access, right? It was write to C of 1, then C of 2, then C of 3, followed by a read of C of 2, C of 3, C of 4. But now if we look at the access pattern, it's write to C of 1, followed by a read to C of 2. We've actually now read from C of 2 in this fused example before we actually wrote to C of 2. We've broken the read after write dependency in that example. Our code, and I would call this a legitimate disadvantage if you apply it incorrectly, our code's now wrong. It would lead to a different result in the version on the right versus the version that we have here on the left. There is all sorts of reasonable ways of modeling the data dependencies in code at this level and determining what set of dependencies can be modified, what type of cache effects will potentially be seen when we apply certain transformations of our loops. That certainly will guarantee correctness after we apply a certain set of transformations, and also can provide some hints as to whether or not performance would be improved when we do so. Right. So in this example, as we see that the dependencies are now broken here. That was loop fusion, where we thought it might make sense to combine multiple different loops together. And we sort of saw that there could be some advantages there. Loop fission or loop distribution is doing the exact opposite, where potentially if you have one very large and complicated loop, and this is only 6 lines here, this is nothing, but you've written loops we all have that have 1,000 lines of code in there. Instead of having one very complicated loop, breaking that loop into multiple smaller loops that we have here. We have to be a little careful how we do it as well with maintaining dependencies between our loops here. This can potentially have very nice performance impact on instruction cache as well, right? By taking this from what could be a very large loop and breaking up into smaller loops, we'll have better spatial locality of instruction memory access, better temporal locality as well. There's also potentially some optimizations that only can be applied within a certain range of instructions. If we have a potentially very large loop body here, that may limit the type of optimizations that are possible here. It does seem a little bit dissonant to say that, loop fusion is an optimization and loop fission is also an optimization. Well, I guess a takeaway is it really depends on the scenario, what is most appropriate for your code base for the compiler to attempt to apply. There's some middle ground of a nice sized loop that allows a certain amount of cache performance and a certain amount of follow-on local optimizations to be applied. We can't say without, analyzing it in the case at hand whether combining loops is a good idea or whether splitting loops up is a good idea. So again, one takeaway is, does applying this transformation to this code, does it improve performance or not? And the answer tends to be, well, it depends. We can always reason about the potential advantages of applying a transformation as well as the potential disadvantages of applying a transformation. And, actual performance profiling is what wins, right? We can think about it. Let's run it. Let's find out if it makes it faster or slower. Loop interchange. This should look a little familiar from our motivating example, where we didn't replace the order of the loops, but we replaced the order of the access pattern. But it leads to the same exact result here. By reversing the order of nested loops, can enable all sorts of follow-on optimizations and also can have really large impacts on cache performance as well. Compilers are capable of doing that analysis. But as we saw, even if the compiler isn't capable of doing it, this is something that we should potentially be able to visualize in our code and see, well, for the programming language, and it is programming language dependent, this modified access pattern is going to lead to much better performance than this other access pattern here. Loop unrolling is a very commonly applied one. where we take the loop body that we have and we replicate that loop body to do multiple iterations of the loop at a single time. This example makes it look a lot uglier than it really needs to look like in practice. But the idea being that if you have a loop that iterates n times, and it's a relatively small loop generally, we can take that loop body and minimize or reduce the number of branches that have to be actually performed here by just replicating that loop iteration and not just doing the I iteration per loop, but doing I and I plus 1 and potentially I plus 2. This example makes it look a lot uglier than it necessarily needs to look here. But if this is our starter loop body here, where it's just an I loop, and we're doing A of I equals some local neighbor computation happening here, the loop unrolled version of it, and there's some bookkeeping code I think we can ignore for now, the loop unrolled version of it, instead of iterating I equals 2, then 3, then 4, instead it's I equals 2, then 4, then 6, then 8. It's hopping by 2 in each iteration here. And for each time now inside the loop, we're executing the I case and the I plus 1 case as well. So we're replicating the loop body, and the compiler is doing it, or we're manually doing it. If we're hand optimizing our software here, we're taking the next, what would have been the next iteration of the loop, and directly putting it in that same iteration of the loop here. This would be unrolling the code by a factor of 2. And it tends to be a power of 2, but that's not actually a requirement that it need be the case. That's our unrolling factor for our loop, right? So this loop is unrolled by a factor of 2. We can easily unroll by a factor of 4 or a factor of 8, where we're taking that many copies of the loop body and doing them all at once, versus having all those additional branches here. That can potentially open up all sorts of other optimizations in our code, both in terms of data reuse, so our locality issues that we've been talking about, as well as the type of parallelization optimizations that can be done on a local level. In one sense, by replicating for our loop unrolling, we've added a lot more local code for the compiler to analyze and potentially apply those other type of optimizations. It's a very common optimization that is applied for squeezing out that last few percent of performance out of our code base. There's a few more. I don't want to bore you guys with this. Induction variable elimination is related to our scalar transformation, where if we know that the loop induction variable itself, we can actually we can reduce it by saying, it's only really happening once. If we know it's a very boring A of I loop here, where the math we have to apply each time around to calculate those new pointers, due to our language providing this ability to index via an array mode here, we can actually make some very small improvements to our performance by replacing that with an equivalent pointer code here. Compilers by and large already do this, right? This A of I is for human readability, right? This is for us to appreciate what we're doing with our arrays and how to manipulate those arrays and how to deal with the dependencies between values that we store in arrays. The compiler by and large transforms the code, and even in 381 when we were doing it, we were doing this transformation and we would convert it to a pointer equivalent where we weren't actually calculating A of I each time. We were just keeping track of where we were in the pointer into that array A and doing the math there. Let's skip another example here. Strip mining is also fine. So I guess one point is there's all sorts of optimizations that look at these loop bounds and determine how to best reorder our loops, how to best peel off parts of a loop, how to unroll certain loops to be able to play with the cache locality, to be able to provide more optimization capability for the compiler for local optimization. A common example that I will briefly mention is loop tiling. And this definitely makes the code look less readable when it's applied. The idea being you take your fairly straightforward and boring loop and you recognize that depending on what the value of n is, that may not be as cache performant as it could be otherwise. And by tiling the loop, we've actually turned it into a more higher dimension version of the problem. And so while the code winds up looking quite worse, we take our doubly nested for loop and we turn it effectively into a quadruply nested for loop here, where instead of looking at it entirely in a row by row or column by column format, by tiling it, we're basically looking at it a tile at a time. as opposed to me belaboring the point here, I'd like you to take a look at that example offline and try to understand what exactly is happening here. But the term itself kind of implies what it's doing, that, again, we can look at the axis pattern for A sub ij and B sub, in this case, B sub ji here, and see that we're going row by row, or we're going column by column. This is a matrix transpose example, right? There's nothing wrong with that example. We talked about cache locality effects and how they can be tricky to deal with. The loop tiling optimization as applied to this loop is recognizing that for some value of n and for some parameters for our cache and our underlying system, by breaking it down into blocks at a time versus attempting to do all n rows or all n columns at a given time, we can lead to performance improvements when we do that. Let's leave things here for now. I'll ask a couple of questions in the learning module associated with this, just for the big picture appreciation of loop optimizations. If you look at your compiler documentation, the GCC you're using for this class, a Clang or other C compilers for other classes, you can see some of the hooks that are provided to actually play around with some of those optimizations. And even for the code that you're doing for the labs for this class, it can be really fun to play with some of those optimizations and see, can you eke out the last few percent of performance improvement. Of all these examples so far today, clearly if there are some obvious data dependencies that you're making worse by your loop structure, improving those could make a difference. The other one to try would be loop unrolling. I think you could see some potential performance improvement by applying that to your code, either manually doing it or passing those command line options to your compiler. Let's leave things for now. When we come back on the flip side here, I'll talk about an optimization that by and large compilers are not capable of doing. So it's not as simple as passing a parameter to our compiler. It forces us to reason about the code that we are writing and look at a specific type of data representation and how that can lead to significant performance improvements depending on the underlying system and the trade-offs we're willing to tolerate in our code in terms of an accuracy perspective. Let's leave things here for now, and looking forward to seeing you on the other side.